वो उधर चली गई ना उधर.
So probably the most fascinating feature of the gravitational bending of light is that its underlying principles are strikingly simple. Photons follow null geodesics in the space-time whose curvature corresponds to the energy-momentum tensor of matter. Outside the localized, non-rotating, uncharged spherical mass distribution, the space-time can be described by the Schwarzschild metric, with Schwarzschild's gravitational radius being a key physical scale proportional to the total mass of the gravitating matter. With the relativistic Hamilton-Jacobi equation, which just re-expresses the energy-momentum relation, one finds the action as function of the coordinates and the constants of motion, which are the energy and the angular momentum. Straightforwardly, from the fact that the derivative of the action with respect to the angular momentum is constant, one finds a relation between the polar angle phi and the radial coordinate r. And in general, the resulting integral does not have an analytic solution, but it can be solved numerically to yield trajectories. It notably diverges at 1.5 times the Schwarzschild radius, sending photons around in a circle, although such an orbit is not stable. If one gets close to a black hole, one can see all the interesting effects that strong gravity has on light, as recently beautifully shown by this image of the supermassive black hole in the center of M87, which reveals the event horizon at the Schwarzschild surface. For light rays that pass at large distances as compared to the Schwarzschild radius, one can expand the action to first order in Rs over r, and for the relation between phi and r, the rising integral has an analytic solution. Photons follow a hyperbolic path with the semi-major axis equaling the impact parameter b of the light ray, and the semi-major axis equaling the Schwarzschild radius rs. From geometry, one finds that the tangent of half the bending angle is given by rs over b, which for small angles is equivalent to the bending angle being twice rs over b. In fact, it was already hypothesized by Isaac Newton in 1704 that gravity should bend light and that the deflection should be strongest at the least distance. A further remarkable feature is that the gravitational bending of light is perfectly achromatic. The gravitational bending angle was famously measured during the solar eclipse of 29th of May 1919 by two British expeditions to Sobral in Brazil and the island of Principe, the latter led by the later knighted Arthur Eddington. The relativistic bending angle was derived by Einstein in 1915, alongside his discussion of the perihelion precession of Mercury, overriding his earlier findings of 1911 that precede the full development of the theory of general relativity, where he proposed half of the amount of deflection. For a gravitating body that can be approximated as spherical, all the physics at distances much larger than the Schwarzschild radius is summarized in the simple equation for the gravitational bending angle, proportional to the mass of the deflector and inversely proportional to the impact distance of the light ray. Everything else that I'm going to talk from now follows just from geometry. No further physics at all. The angular Einstein radius constitutes the single fundamental scale for the bending of light by astronomical bodies. It corresponds to the angular size of the ring-shaped image that is observed if light from a distant background star bends around a massive deflector, usually, but somewhat inappropriately referred to as gravitational lens. That happens to be exactly in between the background star and the observer. The angular Einstein radius itself derives from the Schwarzschild radius, has the relativistic factor 2, and is amended with the relative lens-source parallax, which is a measure of the geometry of the system. We can only see the banded light of the source star if the light gets around the foreground object, which means that its angular radius has to be smaller than the angular Einstein radius. This implies a lower limit to the lens distance, which for the Sun evaluates to 550 AU, whereas an observer nerve is much closer than that. Eddington and colleagues only saw light coming along one path near the edge of the Sun, not passing either side. For all other foreground stars, light rays won't be blocked. For a given mass density, the minimal distance is inversely proportional to the radius of the deflector. And for a rock of 20 centimeter diameter, one finds a more restrictive limit of 100 megaparsecs. The ring-shaped image breaks up into two parts, one inside and one outside the Einstein circle, if the source star is off from the axis that passes through the lens star and the observer. While we lose the rotational symmetry, observer, lens, and source define a plane for the light ray, so that seen from the observer towards the sky, the source and lens star and the apparent images fall onto a straight line. Writing the angular separations in multiples of the angular Einstein radius, we find a simple relation that gives the true source position as function of the image position, and by inverting it, one finds the two image positions as solutions of a quadratic equation. Let's now look at what values characteristic properties take for scenarios that give us observable effects. The galactic bulge is the most promising direction to look at, given that one would like to monitor stellar fields that are dense, so that there are many stars within the field of view of the camera, but not that dense that lots of stars end up unresolved on the same pixel. Moreover, one should choose a direction that ensures that there are lots of intervening stars that could constitute the gravitational lenses. Given that we have to rely on chance alignments, we cannot select the intervening bodies, but need to take whatever comes, following the mass function of stellar and substellar objects. The relatively large number of low mass stars makes red dwarfs of 0.3 solar masses the typical prototype of a lens star, whereas just about 10% are F and G stars. Moreover, a source star in the dense stellar field of the galactic bulge, located a bit behind the galactic center, is about 8.5 kiloparsec distance, while a typical lens star can be found at 6.5 kiloparsec distance. Consequently, for an M-dwarf lens star with 0.3 solar masses, the angular Einstein radius is around 300 microarc seconds. That is far too small for resolving the images. 300 microarc seconds times 6.5 kiloparsec gives 2 AU as its physical size at the lens distance, which actually means that light rays deflected by a star face a good chance to further get close to a planet. Lens and source stars are in motion, with a typical relative proper motion of about 15 microarc seconds per day, which means that rather than a static phenomenon, we see transient gravitational microlensing events, whose time scale, the angular Einstein radius divided by the motion, is about a month. With the mass density, one finds an event rate of about 10 to minus 5 events per year per observed star. As a source passes by the lens star, its images move around the Einstein circle. While we cannot resolve these yet, the fact that the gravitational light bending distorts them results in a time-dependent observable total magnification. This means that gravitational microlensing events come with a photometric signature, the first of which being reported in 1993, which was the result of a massive data processing venture impossible with the computer technology of earlier times. For separations much smaller than the angular Einstein radius, the magnification becomes approximately the inverse of the angular separation in units of the angular Einstein radius. It diverges as u approaches 0, corresponding to a point being mapped to a circle. This would also mean that while both the duration of a photometric microlensing signature and the probability for it to occur are proportional to the angular Einstein radius, that is proportional to the square root of the lens mass, the amplitude is not limited. Larger magnifications are just less probable. However, a limit arises from the finite size of the source star, which reduces the amplitude while increasing the duration. This means that the single duration will become related to the motion of the source star by its diameter, as its angular radius is no longer much smaller than the angular Einstein radius. If one is able to detect deviation as small as 5% in the photometry of stars of solar radius, foreground objects with masses as small as the Moon can be detected, which comfortably includes planets. Given the specific sensitivities of the various techniques used to detect planets, the coverage of planet parameter space, as for example indicated by planet mass and orbital separation, is patchy and far from uniform. Notably, those very regions where we find the solar system planets are amongst the least explored. Moreover, if we look at the location of the identified planets within the Milky Way, we find that the vast majority are within less than 1.5 kiloparsec, with only gravitational microlensing probing along a single line of sight towards the galactic center at larger distances. Given that there are distinct stellar populations, with stars in the galactic disk and bulge having different evolutionary histories and different average properties, we are really not obtaining samples that are characteristic for a galaxy, but mostly probe the solar neighborhood only. How planet demographics look like beyond the Milky Way remains a further open question. The specific characteristics of the phenomena of planetary transits and gravitational microlensing make them complementary for obtaining planet demographics. NASA's Kepler mission has already provided much insight into the planets close to their host stars, whereas a microlensing campaign with the Nancy Grace Roman Space Telescope, formerly called the Wide Field Infrared Survey Telescope, short WFIRST, will explore the regime of planets in wider orbits, and in particular cover planets like those in the solar system, except for Mercury. With the sensitivity extending down to about lunar mass, analogues of the giant moons of Jupiter and Saturn, such as Ganymede and Titan, become detectable. A planetary mass function must, however, not be viewed as a low-mass extension of the stellar mass function. Planets do not form as independent objects, but from the circumstellar disk, so that their demographics will naturally depend on the properties of their host star, most prominently its mass and metallicity. Moreover, planet demographics are also characterized by the planetary orbits, so that a differential mass-radius orbit function has at least 6 parameters, and any planet sample corresponds to a weighted average of the underlying specific stellar population. If we intend to sample a planet population statistics with p parameters, and we want to fit a function to the measured sample abundances sorted into b bins for each parameter, we can work out the required sample size for a desired relative precision kappa. Let's say one sees an indicative functional behavior for 5 bins or more and 20% relative precision. Then a sample comparable of what we have right now, around 4,000 to 5,000 planets, would permit to obtain a function of 3 parameters. For example, stellar mass, planet mass, planet radius, and stellar mass. If we want to study planets as function of both stellar mass and metallicity, we find ourselves restricted to only one property of the planet. For exploring all major 6 parameters, a sample of about 400,000 planets would be required, 100 times larger than what we have right now. This is extremely challenging. Talking about challenging, how far down in mass can one go? As we have seen, the limit is the size of the observed source stars. White dwarfs are an end product of stellar evolution, and they are roughly about 100 times smaller than main sequence stars like the Sun. Observing white dwarfs would push the mass limit of microlensing searches from 1 lunar mass down by a factor 10,000. The downside is that white dwarfs are quite faint, and that a single duration would drop to about a minute, which calls for quite a large telescope to get precision photometry with exposures that last less than 10 seconds. Interestingly, an engineering limit for ground-based telescopes arises from the need to support their weight, which would not be an issue if one assembled a giant telescope in space from smaller parts. Observing short microlensing events on white dwarfs would not only put many satellites and dwarf planets within reach, but would also make asteroids with diameters larger than 200 kilometers detectable, of which the solar system contains about 40. Light would get around such bodies if they are more distant than about 100 parsecs, so that one would be able to explore such within planetary systems throughout the Milky Way. Schudemeyer and Botan-Pyczynski in 1991 not only suggested that planets could be detected by microlensing, but pointed out that more massive companions should be actually easier to detect. For such binary lens systems, one finds extended lines that describe source positions for which the point source magnification diverges, or equivalently, the Jacobian determinant of the lens mapping for at least one of the images vanishes. These constitute caustics of the optical system. A single point mass lens has a point-like caustic at the position of the lens star, that is u equals to 0, which maps to the Einstein circle with an infinite point source magnification. For binary lenses, this central caustic breaks up into a finite diamond-shaped caustic with 4 cusps. More specifically, for any binary gravitational lens, regardless of whether the masses are about equal or whether we have a star with a small planet, there are 3 different caustic topologies, depending on the separation between the 2 lens objects, therefore labeled as wide, intermediate, and close. In turn, the caustic structure of the lens system causes a wide range of possible morphologies of the rising photometric light curve of a binary lens microlensing event, making its characterization far from easy. However, gravitational microlensing events provide a great and yet underexplored source for studying the regime in which planets and brown dwarfs overlap, as well as that of close binaries that are otherwise not resolvable. Caustics are also useful for scanning the brightness profile of the source, given that there is a substantial differential magnification across the stellar disk. For the event Macho 97 bulge 28, it is illustrated how much of the total light comes from each of 10 equal area ring slices, and one sees how in sequence they take their turn as the star sweeps over the caustic. A proper motion of 15 microarc seconds per day and a 3-minute sampling translates into an effective resolution of 30 nanoarc seconds. With stars getting fainter and redder towards the edge, one can also use parametric functions of limb darkening laws, where for each profile function, one finds a universal fold caustic magnification function. If the observed source star is a binary with a near-edge-on orientation towards the observer, the angular radius of its components in relation to the angular Einstein radius determines whether one has an eclipsing or lensing binary. The latter will only occur if one of the objects is a compact stellar remnant, and the first such system involving a white dwarf has been reported in 2014. One actually sees lensing as the white dwarf passes in front of its companion star, but an eclipse as the companion star gets in front of the white dwarf. A Zooniverse citizen science project hunting for black holes as binary self-lensing constituents in the data of the Superwars transit search got underway recently. The motion of the unresolved images not only alters the observed amount of light, but also displaces its observed centroid, which constitutes an astrometric signature of gravitational microlensing events. In contrast to the photometric signature, it is proportional to the angular Einstein radius, and therefore in principle permits a direct measurement of this characteristic quantity. It is also a vector function pointing away from the lens star. If the separation gets large, the image centroid shift drops off far more slowly than the magnification, with 1 over u rather than its fourth power. Therefore, astrometric microlensing signals remain observable for large lens source separations for which there isn't any significant magnification. For small lens source separations, the image centroid shift approaches 0 in proportion to it. That is, where the magnification explodes, the centroid shift turns small. Given that the centroid shift approaches 0 for both large and small separation, there must be a maximum. And in fact, for an angular separation of square root 2 times the angular Einstein radius, a maximal centroid shift of square root 2 divided by 4 theta e, approximately 0.354 theta e, occurs. If one looks at the components of the centroid shift, parallel and perpendicular to the motion of the source star relative to the lens star, one finds that the light centroid shift traces an ellipse. For large u0, the ellipse approaches a circle, whereas for small u0, it approaches a straight line in parallel direction. Astrometric microlensing observations can be used, for example, to measure masses of isolated stellar mass black holes. If they cause a microlensing event, their relatively large mass implies a rather long time scale, so that the observed photometric light curve becomes asymmetric due to a shift in the relative lens source position caused by the Earth orbiting the Sun. This gives a measurable microlensing parallax parameter pi e, which is the lens source parallax divided by theta e, and with theta e measured from the astrometric signature, one directly finds the mass. Moreover, if one can obtain the source distance and proper motion, for example by using Gaia gate data, one finds the lens distance and proper motion as well. That is not only the mass function, but also spatial distribution and kinematics of black holes in the Milky Way, except for the radial velocity, could be extracted from a suitable sample of microlensing events. Just about a century after Eddington, the gravitational bending of light was measured for another star, the white dwarf Stein 2051b, which is in a binary system and the 6th nearest white dwarf known, which means that it's quite bright. From Gaia data, it was predicted that it would approach a more distant star, passing as close at 0.1 arcsecond. Positional measurements were made with HST for several epochs, but the much fainter background star could only be resolved for separations larger than about 0.5 arcseconds. Nevertheless, the shift in position was clearly seen and delivered an angular Einstein radius of about 30 milliarcseconds, which then, together with the measured parallax, provided a measurement of the mass of the white dwarf Stein 2051b. In comparison with the closest angular separation being 3 times the angular Einstein radius, the photometric brightening was never substantial. If we look at the scale in the figures, you might notice that while Eddington measured a deflection by about 2 arcseconds, we measured about 2 milliarcseconds. Despite the fact that it was the gravitational bending of light near the edge of the sun that made Albert Einstein and its theory of general relativity world famous, concluded in 1936 that there's no great chance of observing this phenomenon for any other star. However, 50 years of advance in technology made it possible to materialize on a tiny chance of 1 in a million, and eventually to detect new worlds with masses similar to that of the Earth. While one cannot get around fundamental limitations, and I discussed several of these, overcoming technical limitations is pretty much a matter of time, rather than a matter of principle. Albert Einstein, I'm just 20 seconds. Albert Einstein apparently could not foresee what 50 years of technological advance will bring. So I won't even try. I've shown a few examples rather than giving you a comprehensive discussion, and I would be surprised if there were no further new ideas emerging of how to apply the gravitational bending of light for providing insight on astronomical bodies and phenomena. The most curious effect, as Einstein called it, will continue to provide a valuable tool. Thank you.